Hello everyone, I'm Zhenshu Sun from Monash University. I'm going to present our work on the importance of building high-quality training datasets for neural code search, which was awarded the reusable and available badges from Artifact Evaluation Track. Code search is a vital activity during software development. Recently, deep learning has been widely applied in this area in view of its advantages in semantic understanding of languages. Deep learning models trained with query code pairs can map the natural language to programming language. With a description of the intended code functionality in natural language, a neural code search engine can retrieve a list of semantically matched code snaps from its codebase. Like many other deep learning tasks, code search models are data hungry and require large-scale and high-quality training datasets. However, collecting a large set of query code pairs is challenging. The queries are supposed to be natural expressions from developers, and the code is supposed to be a valid semantic match to the queries. The ideal data source for genuine code queries is the production data from existing neural code search engines. However, these queries are not publicly accessible due to privacy and business sensitivity, so we use text with similar intentions as a replacement. There are two main data sources for neural code search models. The first is GitHub, an open source community hosting more than 100 million repositories. We use the first sentence of the code comment as an alternative to queries, because it usually describes the functionality of the code. And we use the corresponding function as the answer to the query. Developers write comments for their software projects without considering the retrieval purpose, so it can be very noisy to code search model. The second is Stack Overflow, a Q&A community specialized for software developers. When asking about source code for implementing a specific functionality, users would propose a question title to express their intention. These are natural user queries with valid syntax and semantics, and the simple code in the answers serve as a response to the query. Compared with GitHub, queries from Stack Overflow have a significant advantage of being closer to natural user queries, but the quality of the code samples is hard to guarantee. To better understand the quality of the code comments from GitHub, we investigate a GitHub dataset, CodeSearchNet, which is popularly used in current code search research. Surprisingly, we found a considerable amount of noise and unnaturalness in the queries of its data samples. As shown in the figure, 1/3 of its queries contain text features that hardly exist in actual user query. Here are their examples. The features are summarized based on our observation of the dataset and may not be sufficient, so the proportion of noisy data can definitely be higher than 1/3. This goes against a basic assumption of learning algorithm that the training data and the evaluation data should share a similar distribution. The poor query quality has been commonly noticed by many other researchers. For example, the authors of CodeSearchNet point out that the script dataset is quite noisy because the documentation is fundamentally different from queries, and we are unable to know whether the documentation accurately describes the code snap. A survey of code search points out that the quality of this training data may adversely threaten the trained model effectiveness. Besides, another researchers believe that there is a sizable gap between the effectiveness of doc strings and a more query-appropriate supervision corpus. Therefore, improving the quality of the training data is important to the code search community. To improve the quality, first we need to analyze the characteristics of queries. The queries for code search possess specific syntactic and semantic characteristics and can be utilized as key features to distinguish genuine user query from noise. Typical syntactic features include text attributions such as keywords, sentence lengths, and language type, while semantic features are more abstract, implicit, and hard to be matched by simple rules. Here are some examples of noises with syntactic characteristics. To recognize the noise, some initial efforts have emerged, such as simple filtering rules based on the appearance of verbs and noun phrases, keyword uncommonly used in the queries, or the query length. The proposed rules are not sufficient to cover the various syntactic violations, leading to limited improvement. As for the semantic characteristics, these examples widely exist in the code comments, but few such queries would require in this way. And the current rule-based methods cannot handle this sentence. Therefore, a remaining challenge is to recognize the code comments that are semantically unrelated to natural user queries. To tackle this challenge, we propose an automated and effective data cleaning framework that distills high-quality queries from generally collected code comments. The framework is independent to the design of code search algorithm and could be integrated with any of them to improve the quality of the training dataset. It consists of two subsequent filters, a rule-based syntactic filter and a model-based semantic filter. The rule-based syntactic filter is applied to detect the existence of invalid query syntax using a root site, which is very precise, and we leave the fine-grained semantic check to the model-based filter. The core idea of the model-based filter is to filter out code comments that do not look like real user queries. As we introduced in the background, the question title of Stack Overflow is an ideal approximation of natural user queries. It would be great if we can take advantage of both the GitHub and Stack Overflow, and we found that the variational autoencoder can make it. It can learn the semantic features such as the expression style and topic from the bootstrap query corpus, and judge how far away the code comment is from its training data distribution. Here, the bootstrap query corpus is collected from Stack Overflow and serves as a reference for the model. The loss value can be seen as the anomaly score. The lower the loss, the more qualified an input is as a natural query. We compute the reconstruction loss for each code comment and cluster them into two groups. The group with unqualified queries is retained for training, and the group of noises is discarded. Next, I will introduce the detail of this framework. I start with the rule-based syntactic filter. Based on a comparative observation of code comments and user queries, we develop a set of rules to precisely identify syntactically inappropriate queries. We have 8 rules to reject or modify unqualified code comments. As a plugin framework, the rule set is extensible, so we propose 3 criteria that the rule set must comply with. The rules that meet these criteria can be appended to the rule set. The major building block of the model-based semantic filter is the variational autoencoder model. It consists of an encoder and a decoder. The encoder maps the input into a latent variable, and the decoder attempts to reconstruct the original input solely based on the latent features. We sort the comments based on their reconstruction loss in ascending order and return the top-ranked ones. It's tricky to decide an appropriate dividing point. There is a trade-off between the quality and the quantity of the dataset. The less data we keep from the top, the higher the dataset quality. However, A sharp reduction in the data size hinders the performance of the trained cosearch model. This figure shows a theoretical model illustrating the relation between the dividing point and the model performance. We leverage an unsupervised clustering algorithm, expectation maximization forecasting mixture model, to find this dividing point. It is widely used to model the mixed distribution of a dataset. To evaluate our method, we trained two code-search models to observe whether the model performance improves after removing the noises. The first model is DeepCS, which adopts the Siamese architecture. It consists of two neural networks to represent the query and code respectively with independent embedding vectors, while the CRLCS is an interaction-based network, where the query and code are compared directly to generate an interaction metric. The two models are designed with representative architectures among most neural cosearch models. For the two models, we prepare three kinds of datasets. All the datasets are for Java. The datasets to train the cosearch models is the CSNT, containing around 400,000 common code pairs collected from GitHub. The Bootstrap query corpus, which is the training dataset for our VE model, is the question titles collected from Stack Overflow. Not all the titles are relevant to the queries for the cosearch task, so we require the question titles to start with how to be tagged with Java and pass the rule-based filter. Use the code comment to test the model is fair and unfair to our filtering method. So in our experiment, we utilize human annotated validation datasets. There are three widely used datasets: CSNV, NCSED, and CB. Each query of these three validation datasets is paired with several correct code snaps and 999 distractor code snaps. It means, given a query, the cosearch model needs to retrieve the ground truth among around 1,000 candidates. Firstly, we evaluate the effectiveness of our data cleaning solution as a pre-processing step when training neural cosearch models. We have three train sites: the origin CSNT, the filtered CSNT, and the control group, the same size as the filtered CSNT obtained by randomly selecting from origin CSNT. We observe the model performance resulted from training these datasets respectively. We can see that the filtered dataset achieves significantly better results than the other two datasets on all the metrics. Besides, the training hours are also shortened by reducing the training data. Secondly, we evaluate the impact of each filter component and each rule. The two filters are evaluated by ablation experiments, where we mute one filter and observe the performance of the model trained under the other filter. The results show that muting one filter can corrupt the effectiveness of our method, which demonstrates that each filter has a positive contribution. Besides, we conduct a manual inception on the queries accepted or rejected by each syntactic rule and the model-based filter to study their precision in identifying noises. Two annotators are hired to rate how likely a sentence is to be used as a code search query. The rating score ranges from 0 to 2, where 0 means worst and 2 best. After filtering, the likelihood score is from 0.27 to 0.61, and in general, either the rule-based filter or the model-based filter achieve high precision. In the model-based filter, we evaluate EMGMM to decide the dividing point between the qualified and the unqualified groups. To assess the quality of the dividing point, we observe the model performance resulting from alternative dividing points, including fixed proportions and the one decided by k-means. It is clear that the EM-GMM algorithm achieves the best performance. As discussed in the method of the model-based filter, the relation between the data quantity and the model performance should be a convex function. According to its property, if there exists another optimal dividing point, it would locate between the 57.5% and the 75%. Therefore, EM-GMM successfully identifies an optimal solution of the dividing point with an error less than 10%. We provide two applications of our filtering framework, including a proof of concept data cleaning toolbox and a high-quality code search dataset. The toolbox is named as NLQF, Natural Language Query Filter. It is implemented into a Python library with extensible recipe, open source filtering model, and tunable dividing proportion. You can access to its source code at this link. We also collect the methods and corresponding comments from Java repository on GitHub, and filter the obtained data with our method. After filtering, there are around 1 million data points left. We name this dataset as CodeFig, CodePaste paired with the filtered comments. We also compare CodeFig on the query quality with several other datasets currently used in neural code search research. Among all the GitHub datasets, CodeFig receives the highest score on data quality, but there is still a gap compared with the Stack Overflow dataset. Finally, we summarize our contributions. A two-step data cleaning framework for code search datasets, which bridges the gap between code comments and natural user queries, but both syntactically and semantically. Implementation of the framework as a Python library for the code search task in academia and industrial. A comprehensive evaluation of our framework's effectiveness, which demonstrates a significant model performance improvement on 3 manually annotated validation datasets. The first systematically distilled GitHub dataset for neural code search, containing over 1 million common code pairs. And thanks for listening. Please feel free to ask any questions.